You don't need the green thing. I'll give you one later. That's the first thing everybody's going to hear in the video. You don't need the green thing. You'll get one later. Okay, so we want to look at the graphs of logarithmic functions, right? None of you have done log functions before, right? Even you guys in 30 didn't get there yet. So graphs of log functions. So what is a log function? It's a function, so a logarithmic function, logarithmic function, let's say, is of the form y is equal to a log base b. Okay? So log functions have bases just like exponential functions have bases. Right? So we do an exponential function like 2 to the power of x. The 2 is the base. Log function, same thing. It's got a base. And so that b is written subscripted, log, and then you write it small and underneath. Okay? So that's called log base b of x. So y is equal to a log base b of x. A can't be 0, right? Because it would just wipe out the whole thing if it were. So, b has to be positive and greater than 0. No, so b is greater than 0, and b cannot be 1. Okay? So the base of the log function, just like the base of the exponential function, right? When we did exponential functions, y equals a times b to the x. The b couldn't be negative, and the b can't really be 1, right? Because if it's 1, then the whole function is just 1, and that's just kind of boring. It's a straight line. So logarithmic is a constant. Okay, so we got y equals a times log base b to the x. That's the form of a logarithmic function. Mostly we deal with what are called common logarithms. Okay, so common logarithm. So we'll just lay the groundwork here, and then we'll go look at the graphs. So a common logarithm is written, well, a common logarithm has a base of 10. Okay, so it has a base of 10. And it's written like this, and is written without a base. So if you see a logarithm and there's no base down here, then it's base 10. Just same as when we do a square root, we don't put anything in the index. So if we want to do cube roots, we got to put a little 3 in there. Fifth root, we got to put a little 5 in there. If we don't write one, and then we know it's a square root. So if there's no base written, so no base written, then it is base 10. And is called a common logarithm. Okay, so a base 10 log. That's the one your calculator has. You have a key on your calculator that says log. That's what it's doing. It's doing a base 10 log. Okay? So y equals a log 10x, and y equals a log x are the same. Okay, so no base written, it's base 10. Okay, and then you get to use your calculator because the key on your calculator does, the one that says log, log, that's a base 10 log. Okay, let's graph this thing. So we're on page 412 in our books, right? So we're just going to kind of follow along with what's going on in the book there, and we're going to do the stuff that's there. You can follow along with your graphing calculator, okay? And I'm going to do this in Desmos, or not. Okay, so we want to take a look at the graph. So we're going to do this, investigate the math. There's some definitions in there as well, also on 412. Randy came across a new type of function in his chemistry class. He learned the pH of a solution is determined by a logarithmic function, right? This is on page 412 up at the top. He wondered how the characteristics of these differ from the characteristics of polynomial and exponential functions, right? So we've looked at polynomial functions, right, in terms of domain, range, end behavior, all that good stuff. And we've looked at exponential functions, same thing, domain, range, end behavior, all that kind of stuff. We've graphed polynomial functions, we've graphed log functions. Okay, is the heat on? Is it going to melt that phone? On your calculator you have base 10, so you should graph y equals log 10x. Go into y1 and graph log 10x. And I'm going to do this on here. I'm just going to go y equals log x. Okay? And I do this here because this is much nicer to look at, right? It's got a nice scale on it. We can see that we have, what do we have? An x-intercept of 1. Is there a y-intercept? What do you think is happening down here? So if I zoom out, and again, and again, and again, do we think that this thing's going to cross this line? No. So that's an asymptote line, right? So the y-axis down here is an asymptote. Let's zoom back in because we don't really want to be that far out. That'll work. Nice scale. Okay, so we've got some characteristic there. Now, maybe we want to change this, right? So Randy tries stuff. He graphed 2 log 10x. So let's do that. And the thing is, we'll graph them all on the one thing, right? Now you can graph them, again, you could graph all 3 on one on your calculator. So I'm going to enter a new expression, which is y equals 2 log x. And at the same time, let's throw in y equals 5 log x, right? Y equals 5 log x. And what we want to look at is, okay, so what do they have in common, right? We're going to go to page 413. We're going to start to answer these questions, right? Okay, so we've got all 3 up here. They're in different colors. I don't know if I can write on this, but I can. So this was y equals log x. This was y equals 2 log x. This was y equals 5 log x. And I just write on there because the screen isn't showing the colors at the side there, right? So I'm just labeling them myself. All right, top 413 saying, what are the characteristics of the log function of the form y equals a log base b of x, where b is equal to 10, or b is equal to e. So remember e, we didn't actually test e, right? But e was the base of the that value. It's actually, e is called the base of the natural log. So we're going to look at that as well. And a is a real number, okay? So we can put any number in for a, except 0, right? If a is 0, then the whole thing disappears, because your expression will just end up as 0. Okay, A, use graph calculator to graph the log function, y equals log base 10x. On the same axes, graph y equals 10 to the x. Oh, okay, so on the same axes, so I'm going to disappear these other 2 for a second. Okay, and we're going to graph on the same axes that say graph y equals 10 to the power of x. Y equals 10 to the power of x. Okay, and okay, I'll leave that like that. Now, for thems of you, what's done 30-1 for any length of time, what do you say about these 2 functions? How are they related? It's reflection in the line. It's reflection in the line. Sorry? Y equals x. Here, let's just graph y equals x. Okay. So, some people did 30-1 have done transformations, and this is a type of transformation, right? And it's actually a type of transformation where you interchange x and y. right? I mean, so what this is, it's a reflection in this line. If you look at these two graphs, if this were a mirror, then this is the reflection. Y equals 10 to the x is the reflection of this line. That says that these are inverse functions, right? And the way you get an inverse function is, let's do one more here. So an inverse function, how do I do the inverse of this? Y equals 10 to the x. What would we do? Interchange x and y, right? So we would write x equals 10 to the y. Okay, let's graph x equals 10. So watch, we've got 3 graphs on here, right? And now I'm going to graph x equals 10 to the y. Tell me what it does. Okay, where is x equals 10 to the y? Here, I'll go over here, I'll hide it, and then I'll reveal it. Okay, so now it's gone. Oops, no it's not. Okay. Okay, now it's gone. Now it's back. Now it's gone. Now it's back. Now it's gone. So where is it? It's on the red line. So these two things must be the same, right? X equals 10 to the power of y is the same as y equals log base 10 of x. Okay? Those functions are the same. X equals 10 to the y and y equals log base 10 of x are the same function. The inverse function is y equals 10 to the power of x, right? These guys are inverses. Okay? How do you know? Because you've interchanged x and y, right? If you interchange your x's and y's, you have inverse functions. And this function is really this. So y equals log base 10x is the same as, so let's make a note of that. Let's go to a new page. So y equals log x and x equals 10 to the y are the same function. Okay, they're the same. We saw that on the graph, right? We turned it on, turned it off, turned it on, turned it on. Yeah, it's the same line, right? So they're the same function. Okay, and they are the inverse of y equals 10 to the power of x. Okay? So one way we do the inverse is by interchanging x and y. The problem is we don't like our functions written in the form x equals, right? They're not really functions, right? We need to write them in the form y equals. And this is how we change from x equals to y equals, right? By introducing a word. We should have used a symbol, right? Because you're okay with square root symbols, right? So I know what that means. So maybe we should have had a fancy symbol instead of using the word log, but we didn't. Okay? So we just used the word log. Okay? And this is how we rewrite this so it's in the form y equals instead of in the form x equals. Okay? So, yeah, where were we here? So we graph, Randy chose 3 functions of the form y equals a log base 10 of x. So let's go back here. I think we can, well, we could leave that or get rid of it. I can get rid of the line, right? We're not interested in the reflection anymore. And let's bring these 2 guys, we can get rid of this guy and bring these 2 back. Okay, so there's our y equals log x, 2 log x, and 5 log x. Part C on page 413. Examine the graph of each function and state the following characteristics. Okay, how many x-intercepts are there? Okay, there's 1. What is the x-intercept? 1. Does it change for any of these guys? No, right? So we just have an x-intercept of 1 regardless of the value of a. Y-intercept. Y-intercept? Okay, so let's, new page, characteristics. so there is one x-intercept whose value is 1. Right? There's an x-intercept that occurs at 1. So remember, when we talk intercepts, we're not talking about a point. We're talking about a value. Right? What's the x-intercept? 1. Where does the x-intercept occur? At the point 1, 0. Right? But we never mention that. When we talk intercept, it's just the value. Y-intercept, what do we say? What was the y-intercept? There is none. Okay, what else do they want? The end behavior. Okay, where are you going? Where do we start? Quadrant. Remember, we do end behavior, we go left to right. Quadrant 4 to quadrant 1. And what's it doing? Increasing, right? So we have quadrant 4. From quadrant 4, right? So we're going from, so end behavior. Quadrant 4 to quadrant 1, increasing. What else? The domain. What is the domain? X is greater than 0, right? We say that because you got no x's, right? We're not going through the y-axis, and the y-axis is where x is equal to 0, right? We say, well, yeah, you're not hitting it, and you're not going through it, so it's x is greater than 0. So domain. Hang on. Set of all x such that x is greater than 0, and the range. Y. Sorry? Speak up, old ears. Real numbers, right? Because it's going quadrant 4, which is down forever, to quadrant 1, and it's increasing. So it's an element of the reals. How else do you know this, for them of you what knows this? Since they're inverse functions, don't do that. I'll hand them out, trust me. You keep it, but just don't get one when I go to hand them out. You don't need it yet, really. Since they're inverse functions, then what happens with domain range of inverses? They just sort of flip, right? Because you've interchanged your x's and your y's. So what was the domain of the exponential function? X belongs to the reals. So what's the range of the logarithmic? Y belongs to the reals. What was the range of the exponential? Y is greater than 0. Which means the domain of the logarithmic is x is greater than 0, right? Because we've interchanged the x's and y's. Okay? Blah, blah, blah. What else? Okay, what's next? Examine the graphs you created in part B. I think we've done that. As you move from left to right, okay, we did that. Choose 3 new functions of the form y equals a log x, where a is less than 0. Okay, so we want to graph 3 where a is less than 0. Go back. So why don't we just change this from 2 to 1/2. And we'll change this from 5 to 1/5, right? Then they're less. Did I say, wait, did I say less than 0? You say, wait, is that, oh, let's change it from 2 to -2, and from 5 to -5. And from 1 to, so let's just put a negative in front of all 3 of these guys, right? So we'll go up here and we'll throw in a negative. Oh, so look what happened. Okay, and I'm going to unshow this now. And let's throw a negative in here. So watch what happens, right? You can see where y equals log 2x here is, and what happened? And what happened? So what happened? For them of you what knows transformations, what do we just do? And you thought those days were over. Okay, let me flip this one back and forth. How do I do that? I want a backspace. All right, backspace. Ta-da. What's going on? It's a reflection in the You got to remember that much, right? I mean, you made it through these first units. So what do? When y is replaced with negative y, it's a reflection in the x-axis, right? Okay. Now, we don't really need you don't need to know that, right? But it's interesting. So some of you guys can make a connection with some prior learning and say, okay, I see what's going on here, right? That it's a reflection in the y-axis. For the rest of us, we're just going to look at it and say, okay, so what characteristics changed? So let's take a look at the characteristics again. X-intercept, did it change? No, same, right? There is 1 and its value is 1. Y-intercept? None. Domain change? Okay, let's look at domain and range. Domain? It's still x is greater than 0. Range? It's going from high and it's going to go down to low. So what did change? What's the one thing that changed? The end behavior changed, right? So we're going to modify this. The end behavior is quadrant 4 to quadrant 1 increasing if a is greater than 0. And the end behavior is quadrant, okay, what's this end behavior? 1 to 4, right? So the end behavior is quadrant 1 to quadrant 4, and it's doing what? Decreasing if a is less than 0. Okay, so that's a big thing we got to keep in mind, right? And what we're going to do is you're going to be presented with graphs and asked, is a greater than 0, is a less than 0? Or, you know, here's 4 equations, here's 4 graphs, match them up. 2 of them are exponential. Okay, by now you should know what an exponential graph looks like, right? The a value is the y-intercept. It's increasing if b is greater than 1. It's decreasing if it goes quadrant 2 to quadrant 1, right? So exponential are easy. They're always going quadrant 2 to quadrant 1 no matter what. Logarithmic, okay, they're from quadrant 4 to quadrant 1 if a is greater than 0, and they're quadrant 1 to quadrant 4 if a is less than 0. And, you know, obviously if you're going quadrant 1, you're increasing, and if you're going to quadrant 4, you're decreasing. Okay, make sense? Should have said something. Talk about what? It's because they're out in the hall. Okay, what else do we want to do? Back to 413, to our investigation, right? And keep in mind, I mean, you can replay this anytime. You know, if you need to go through this. Again, examine graphs, blah, blah, e less than 0. On a new screen, graph the natural logarithmic function y equals ln x. Okay, so we're going to go back here. We're just going to wipe everything out. Okay, and we are going to graph y equals, and you have a key on your calculator, right? Your ln key is right below the log key. So it must be important, right? It has its own key on the calculator, like times and plus and minus and divide and squaring. So it's obviously an important function, right? Because it's not it's not in some sub menu, right? It's right there. Try and say some sub menu 5 times fast. Okay, so it's right there, and it's called, I call it ln. A lot of people call it ln, ln, because, you know, there's no AW in there, but it's pretty close. In which case it should be green, really, right? It should be green because it's a ln of x. But now it's kind of brown, so maybe this is, you know, red, kind of, I don't know. Some people say ln. I don't know where they get that from, but some people say ln. And they want us to also graph what? Y equals e to the x, right? This is the exponential function, e to the power of x. Okay? And you got one of those too, right? You have an e to the x. It's the second function of the ln key, right? That's the one that says e to the x. Just like you have a 10 to the x, which is the second function of the log key. So they're important, but not as important. Okay, how are these two related? They're inverses of each other, right? Just like 10 to the x and log x. So we have e to the x and ln of x. So these are inverse functions. Okay? Inverse just means it undoes it, right? So like an inverse function. So I have a function that converts Celsius to Fahrenheit, right? I got a friend coming out from the States, they just don't understand what the temperature is. So you say, okay, we'll convert Celsius to Fahrenheit. If you have a function that converts Fahrenheit to Celsius, that's the inverse, because it'll undo it, right? It'll undo that function. Just like if I'm flying without a rope here, so y equals the ln of e to the x. See, if I graph the ln of e to the x, if I undo the e to the, they just end up with x, right? So the input was x, I did e to the x, then I did the ln of that, which is the inverse function. It just gives me back your original input, which is x. And I graph that, and you can see, hey, these are inverses, right? Because it's a reflection in the line y equals x, which you don't have to know, right? But it's good to see. And for those of you that can relate to it, it's kind of like, oh, okay. Then you can go see your 30-1 teacher and say, hey, we related something back to that stuff we did that I hope to never see again. Okay? All right, and what we're going to do with this ln x. On a new screen, graph the function y equals ln x and two other functions of the form a ln x. Okay, so let's just go and we will graph. How about 2 ln x? Oh, I'll pick a number, any number. What number would you like? 8. 8 ln x. So there's 8 ln x and one more. 6. Okay. Too much pressure. I should pick 2 numbers. Okay, so. Look at that. We got more space, and apparently we got 55 minutes. So we got to finish this in less than another 38 minutes. Right? Which you're hoping, God, let it be over soon. All right. So how does all this compare to the characteristics? Let's go back and describe the characteristics. So how many x-intercepts? So we're looking at G. 1 x-intercept, which is where? At 1. Okay? So same. The y-intercept. The y-intercept. There isn't one. Thank you. The end behavior. Quadrant 4 to quadrant 1, increasing. The domain.
X equals greater than 1. 0.
Greater than 0. The range.
Range is everything.
Y is set of all y such that y belongs to the real. So there is no difference in these characteristics, be it a base 10 log or a base e log, right? All of this is still the same, which then begs the question, if I change a to less than 0, will it change from quadrant 1? What do you think? So if we change the a's to negative, which has got to be the next part, right? Yeah, it's like I at the bottom. So if we change the a's to negative, what's going to happen? Did our x-intercepts change? Did our y-intercepts change? Did our domain change? Did our range change? What changed? End behavior, which is now quadrant 1 to 4, decreasing because a is less than 0. Okay? So that's the big stuff to remember, right? You got to remember these characteristics, right? 1 x-intercept at 1. No y-intercepts, and behavior depends on the a value, whereas in the exponential function, it was the y-intercept that depended on the a value. So there are some differences between the two. You got to be able to recognize this function is exponential, this function is logarithmic, and which one it could be given a graph, right? So given equations and then given a graph, you need to be able to recognize, oh, that's an exponential function where b is greater than 1, so that's this graph. That's an so you don't have to go into details, right? Like if you're given 4 graphs and it's obvious this one's exponential where b is greater than 1, this one's exponential where b is between 0 and 1, this one is logarithmic where a is positive, this one is logarithmic where a is negative, then you don't have to go in, well, what's the value of a and b, right? Who cares? right? You got 4 choices. They'll each match up with one graph. All right, what else is in this book? Reflecting. Ha! We reflected in the line y equals x, and we reflected in the x-axis. But that's not the reflection they want. So it's just be able to compare these logarithmic graphs to exponential graphs, right? Based on your observation, so this is on the top of 414. Which characteristics of logarithmic differ? I'll let you reflect on this yourself, right? There's a little reflection you can do. Apply the math, connecting the characteristics of an increasing log function to its equation and graph. All right? I have confidence that you can now do this, right? So you could read through example 1 on your own and be able to say, yeah, okay, I can figure that out. Example 2, connecting the characteristics of a decreasing natural logarithmic function to its graph, and I have complete confidence that you'll be able to do that. And on 417, example 3, matching, I have complete confidence you'll be able to do that. And on 419 is the key ideas, right? Summary, which you should always be looking at any section we do, right? You want to be able to look at this stuff and say, what are the key ideas? What am I supposed to know? Like, so that, you know, because you could ask me that on the test, or what are the characteristics? Because the questions are going to be based on these key ideas, right? On the idea of, well, how does the A value affect a log graph? What's the domain of every log graph? What's the range of every log graph? Et cetera, et cetera. Okay, so just make sure we've covered everything off that we need to cover off, right? We did natural logarithms. We graphed them. We have stated all the characteristics. Okay, so I think we're good to go, right? Before we run